Hi, I'm Braden Barbary, and this is my Physics 2212 Lab 6 video on magnetic molasses. So for an introduction, the point of this lab was to explore the interaction between a falling bar magnet and a conducting tube. The experiment was measured both physically and computationally. In the end, both the in-person experimentation and the GlowScript code gave around a 1.3 second fall time. In the lab, the bar magnet was the system, and the conducting tube and gravity both acted as parts of the surroundings. So, the physics principles used in this lab were Newton's second law of motion, which gives the change in acceleration, and this change is proportional to the change in the force, and that is this formula here. There was Faraday's law. This law gives the induced EMF as a result of the change of magnetic flux over the change of time. And there's this negative n here, which is the n is for the number of loops in the system, and it's a negative to help the sign change. Then there's Biot-Savart's law, which this law gives the magnetic field a point due to a current. In the procedure, to do the experiment, a cardboard tube was wrapped with many layers of aluminum foil. Then a bar magnet was dropped from the top of the tube while a person was measuring the time the magnet was in the tube with a stopwatch. After 5 drops, the average time the bar magnet was in the tube was found to be 1.35 seconds. Coding. Above are the constants used in the lab. The first image is the properties of the tube used with the length of the tube, the width, and the radius of the tube. And all of these are in meters. And then the second image is the properties of the magnet, which we already found in Lab 3, which has the mass in kilograms and the magnitude of the magnetic dipole moment. Some more coding. So this piece of code above calculates the magnetic field of the bar magnet, and this piece of code calculates the flux through each ring as the magnet is falling. And another slide of code. 3 images above are used to calculate the total force. This force is then used with Newton's second law to find the change in acceleration. And this is the force of the gravity, the force of the gravity on the magnet, the force of the magnetic field, and the net force, which you add them both together. And for the coding output here, this shows the magnet falling through the tube, and this is a velocity to time graph, and it shows that the magnet left the tube in 1.337 seconds. What if number 1? What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Due to Ohm's law, which is potential difference equals the current times resistance, decreasing the resistivity would cause the current to increase. This would create a stronger magnetic field, which would cause the magnet to fall slower. What if number 2? What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The amount of ring currents in the tube would decrease, which in turn would decrease the magnetic field, causing the magnet to fall quicker. Assumptions and possible errors. Assumptions. The bar magnet had the same magnetic dipole as the magnet used in Lab 3, and a possible error was that the timing of the magnet falling could be off due to human error. The true result would likely be a shorter amount of time than found because there was always a delay between when the magnet was seen falling out of the tube to when the stop button on the stopwatch was actually hit. And in conclusion, the measured values found through the experimentation and the values found through the closed script code were able to match very nicely with only a 0.02 second difference. Thank you for listening.